We're going to look at the trig identities, or more correctly named the Pythagorean trig identities. There's our circle. I've drawn a right angled triangle in the first quadrant there. The circle's radius 1, and the adjacent side is the x value, and the opposite side there is the y value. Now, we know the equation of that circle is x squared plus y squared is equal to 1. We know that to be true. We could also show that actually the y value would turn out to be sine theta, and the x value would turn out to be the cosine of theta. Well, if I substitute that into our equation of a circle, we get our first result. Sine squared plus cos squared will always equal 1. Called the Pythagorean trig identity, I guess because it also satisfies Pythagoras' theorem when you think about it. Like x squared plus y squared would equal 1 squared. Now, how do we get our next one? We divide everything by sine squared. Well, sine squared divided by sine squared is of course 1. Cos squared divided by sine squared would be cotan squared. And 1 divided by sine squared is cosec squared. And that creates the second of our trig identities. So 1 plus cot squared is cosec squared. For the third one, instead of dividing by sine squared, we'll divide by cos squared. Sine squared over cos squared is tan squared. Cos squared over cos squared is 1, and the reciprocal of cos squared is sec squared, and we get the third of our trig identities. So in fact, the 3 trig identities are actually the same identity, just written a different way. So they are the 3 that we can use. There's also a really useful relationship. Always remember that little one, that the tan of theta is sine theta on cos theta. You can always use that in your solutions. Here's a question. If cos theta is 3/4 and tan theta is negative, find sine theta. Now, they traditionally put this sort of question with trig identities. I don't know why, because I think that's a silly way of solving it. What they're actually expecting you to do is go, well, cos theta is 3/4. I can substitute that into sine squared plus cos squared is equal to 1. I can then work out what sine squared is. From there, I can work out sine. Oh, is it plus or minus? And that's where the other bit of information comes in. I think that's a long way about going. The most sensible way is to just do this. They told me cos theta is 3/4. There's my triangle. Pythagoras, I can work out the other side. And now I can just read off the triangle. Tan theta is negative. Cos theta is positive, we'll notice. Therefore, we're in which quadrant? So sine theta should be, so we read off and we get minus root 7 on 4. I do think that's a little bit quicker than using sine squared theta plus cos squared theta is equal to 1. Well, let's actually use it then. We'll start with a very, very simple one. One would hope when you see 1 minus cos squared theta that we can look at that straight away and say what the answer is. But just imagine you can't. So you look at this, you say, oh, 1 minus cos squared, I've got to change this into something. The nice thing about those trig identities is they all involve different trig ratios. So you can't pick the wrong one. So I must be using the one that involves cos squared. And if I look at the one that involves cos squared, I can see that if I made cos squared the subject, I'd get 1 minus sine squared. And then expand that all out and we get sine squared. It does, of course, beg the question that if you realise cos squared was 1 minus sine squared, why didn't you realise 1 minus cos squared was sine squared? But anyway, that's theoretically how you could do it. I'm not suggesting that you would. I'm sincerely hoping you would look at 1 minus cos squared and go, oh, that's sine squared. Sec squared minus tan squared. So again, don't see it straight away. We say, hang on, I've got a trig identity. It says that 1 plus tan squared is sec squared. Well, it's already got sec squared as the subject. So I'll sub in for sec squared, 1 plus tan squared, and oh, it's just 1. Okay. Tan theta, cos theta. Hang on, there's no mention of squareds in this. So if ever I'm unsure, I'll go back to, let's change everything to sines and coses and let's see what happens. So the tan theta we change to sine on cos. The cos thetas cancel and I'm just left with sine theta. Let's get to the more interesting questions where we actually have to prove some stuff. So we're going to prove this one. 2 sec squared alpha minus 2 over 4 tan alpha is the same as tan alpha on 2. I will start with the left-hand side now. So I'm going to start with this piece of algebra. I want to end up with tan alpha on 2. So what am I going to do to it? Well, I have a trig identity that involves sec squared. Sec squared is 1 plus tan squared, so I'll sub in for that. Expand that out, tidy it up. Tan divides into tan squared. Oh, 2 and 4's got a common factor as well. And I get the right-hand side. Here's the important thing though. When you're doing these sort of problems, okay, You are doing a proof, so you cannot treat this like an equation. You can only treat it like an equation if you know it is a fact. Now, we don't know this is a fact. We're trying to prove it. So we can't do that. So I went with the first one. I started with what was on the left-hand side, and I end up showing it was the same as the right-hand side. You could have, if you had wanted to, start with the right-hand side and then show it's the same as the left-hand side. And then, of course, there's a third option where you work on both sides independently. So you might start on the left-hand side and you keep going and you get to a point where you go, geez, I don't know if I can go any further with this. I don't know where this is heading. So you leave that alone and then you start working with the right-hand side. And you keep going and keep going. And hopefully, in your working out on the right-hand side, you end up with a line that is the same as what you had in your other one. Now, once you've got two lines that are the same, at that point you can then say, well, hang on, these two things must be the same. Therefore, well, for want of a better word, left-hand side must equal right-hand side. But never move things. So I'm going to get rid of the fractions and all that, because all you'll ever do with something like that is prove some statement like 0 equals 0 or 1 equals 1. And whilst it is true, it's not a proof. Just to show you that I could have started with the right-hand side. Here we go. I'll start with tan alpha on 2. Now, what am I going to do with that? Well, I'm going to change that to tan squared alpha on 2 tan alpha. Why do that? Well, I'm keeping an eye on what I'm trying to prove. And notice there's a tan alpha in the denominator. Now, what I'm starting with doesn't have a tan alpha in the denominator. So that was the first thing I did. I'll just put tan alpha in the denominator. Well, that means I've got to put it in the numerator as well. But now that I've got tan squared, I can say, hang on, I've got a trig identity. Tan squared is the same as sec squared minus 1. And now we're getting closer to what they want. Because if you go back to see what it was, the number on the bottom is actually 4, not 2. So if I now multiply top and bottom by 2, I've got the left-hand side. So you could have started with the right-hand side. Don't think it's as easy as starting with the left-hand side in this particular case, but sometimes it will be easier to start with the right-hand side. And what the heck? Let's do it this way. Remember I said, don't treat it like an equation. And now you're going to look at me and say, you're a hypocrite. You just treated that like an equation. And the answer is, no, I did not. Notice I'm still saying I want to prove this. I haven't started my proof yet. I've just changed what it is I'm trying to prove. That's okay. So I've moved everything to one side of the equation. And I've said, I want to prove that this is equal to 0. Because if I can come up with a statement that this is equal to 0, once I know that's a fact, then I can move that to the other side and say, well, this must equal that. So I want to prove that this is a fact. So I'll start with that left-hand side. And I'll make it all one fraction. The common denominator would be 4 tan alpha. But on the top, I'll now end up with 2 sec squared alpha minus 2 minus 2 tan squared alpha. But sec squared is 1 plus tan squared, and we end up with 0. So I have proved that that is equal to 0. Now that I know that is a fact, I can go, thus, if I move this over, it must be true. And so I've proved my identity. That's a technique that's used very often in equations, because often it's easier to show something's always positive or something's always negative, but there's nothing stopping you using that idea for equations as well. Let's have some fun playing with our trig identities.